Hi students, today we will discuss the fifth module of our subject computer-aided design and analysis. The CAD system is extensively used in mechanical engineering and manufacturing industries. You all know that various design related tasks performed by the CAD system are geometric modeling, engineering analysis, design review and evaluation, and automated drafting. From module 1 to 4, we studied about geometric modeling and different methods of representing the objects in geometric modeling. And now, let me introduce you an interesting topic in engineering analysis, that is finite element method, FEM, sometimes referred to as finite element analysis, FEA. So FEM is a computational technique or numerical method used to obtain approximate solution of boundary value problems in engineering. Boundary value problems are also sometimes called field problems. The field is a domain of interest and most often represent a physical structure. If we consider a structural analysis, we can say a physical structure as a truss as a physical structure. The field variables are dependent variables of interest governed by differential equations. Field variables, for example, displacement, temperature, etc. The boundary conditions are the specified values of field variables on the boundaries of the field. So, a boundary value problem is a mathematical problem in which one or more dependent variable must satisfy a differential equation everywhere within a non-domain of independent variables and satisfy specific conditions on boundary of the domain. In simple terms, FEM is a method for dividing up a very complicated problem into small elements that can be solved in relation to each other. Depending on the type of physical problem being analyzed, the field variables may include physical displacement, temperature, heat flux, fluid velocity, etc. FEM is useful for problems with complicated geometries, loadings and material properties where analytical solution cannot be obtained. The technique has variety of application and has been used on problems involving stress analysis, fluid mechanics, heat transfer, vibration, etc. The finite element method was first used in 1956 for aircraft structural problem analysis, and later on within a decade the potentialities of this method for the solution of various types of engineering and applied science problems were recognized. Let's see how FEM works. FEM uses a complex system of points called nodes which make a grid called a mesh, and this mesh is programmed to contain material and structural properties in which define how the structure will react to certain loading conditions. The nodes, the complex system of points called nodes, are assigned at certain density throughout the material depending on the anticipated stress levels of a particular area. Regions which receive large amount of stress usually have higher node density, and the mesh act like a spider web, and this web of vector is what carries the material properties to the objects, creating many elements. In finite element method, the solution region is regarded to be composed of many small interconnected subregions called finite elements. Within each element, a feasible displacement interpolation function is assumed. Stress strain computations at any points in that element are then performed, following which the stiffness properties of the elements are derived. Elemental stiffness are then assembled to represent the stiffness of entire solution region. This is how an FEM works. So it contains or it involves general steps. So let us see what are the steps involved in FEM. The first step is discretization of the structure, which means that elemental division. So we will divide the structure into small elements, that is called discretization, and after discretization we will number the elements and nodes, and after numbering the nodes and elements a displacement function or interpolation function will be selected, and after the selection of displacement function, by using strain displacement relationship and stress strain relationship, we will define the material behavior, and then we will derive elemental stiffness metrics and equations. For each element we will find the stiffness metrics. After the derivation of elemental stiffness metrics, we will assemble this equation to a global equation, So after attaining the global equation, we will apply the boundary condition. By applying boundary condition, we will get some unknown displacement, and by getting the solution for those unknown displacement, we can compute elemental strain and stresses from the nodal displacement, and at last we will interpret the results. These are the steps, general steps involved in FEM. Certain steps in formulating a finite element analysis of a physical problem are common to all such analysis, whether it is structural analysis, heat transfer, fluid flow, or some other problems. We can say that there are three phases in FEM. The first phase is pre-processing phase, quite generally described as defining the model, and it includes defining the geometric domain of the problem, defining the elemental type, material properties of the element, geometric properties of the element like length, area, etc., element connectivities, physical constraints, that means boundary conditions, defining the loading. This all comes under pre-processing phase, that is model definition. So this phase is, or this step is critical. The next phase is solution phase or analysis phase. During solution phase, the finite element software assembles the governing algebraic equation in matrix form and computes the unknown values of primary field variables. The computed values are then used by back substitution to compute additional derived variables such as reaction forces, elemental stresses, etc. As it is not uncommon for a finite element model to be represented by tens or thousands of equations, special solution techniques are used to reduce data storage requirements. For example, for static linear problems, a wavefront solver based on Gauss elimination is commonly used. Just for example, I mentioned it. Next, the third phase is post-processing phase. So, analysis and evaluation of the solution results is referred to as post-processing phase, and this post-processor software contains sophisticated routines used for sorting, printing, and plotting selected results from finite element solution. So examples of operations that can be accomplished uh, during this phase includes um, sort element stresses in order of magnitude, check equilibrium, or plot deformed structural shape, animate dynamic model behavior, or produce color coded temperature plots. These all can be done in post processing phase. While solution data can be manipulated many ways in post processing, the most important objective is to apply sound engineering judgment in determining whether the solution results are physically reasonable. That is the main objective of this phase. So as I mentioned, there are three phases: pre-processing phase, which includes discretization and numbering of nodes element; analysis phase, in which a displacement function is selected, and after that we will derive the elemental stiffness matrix, we will assemble the equations applying boundary conditions, and we will find the unknown displacement and other elemental stress and strain. And the third phase is post processing phase, in which we will interpret the result. So discretization, as already mentioned, discretization is a method of subdividing a structure into a convenient number of smaller components. Between solid modeling and finite element analysis lies an important intermediate step of mesh generation. Mesh generation as a pre-processing step to FEM involves discretization of solid model into a set of points called nodes, on which numerical solution is to be based. This I already mentioned. So finite elements are then formed by combining the nodes in a predetermined topology, such as linear, triangular, quadrilateral, etc. Discretization is an essential step to help finite element method solve the governing differential equation by approximating the solution within each finite element. The process is purely based on geometry of the component and usually does not require the knowledge of differential equation for which the solution is sought. The accuracy of FEM solution depends on the fineness of discretization. So that we can say a finer mesh, the solution accuracy will be better. You can see a continuous domain on your left side figure and discretized domain, that is meshed domain in right side figure. The concept of FEM is all about discretization, dividing a big structure into small discrete blocks, and there are two type of discretization. Natural discretization is there and artificial discretization is there. In any structural analysis, truss is considered as a natural system. The various members of truss forms the element, and these elements are connected at various joints known as nodes. In the artificial discretization, a single mass of material as found in forging, concrete dam, deep beam and plate are generally called as continuum. There are three elements exist: triangular element, rectangular element and quadrilateral element. So after discretization, we will study about numbering the nodes and elements, isn't it? So before that, we will get into the types of elements. What are all the types of elements? The first one is one-dimensional element, the second one is two-dimensional element, and third one is three-dimensional element. One-dimensional element. One dimensional element, also referred as line elements, which is often used to represent members which are too long compared to the measurement of the cross section. Two-dimensional element are also referred as shell element or plane element, which is often used when thin sheet structures are under bending deformation. And three-dimensional element are also referred as solid elements, since actual tasks deal with the three-dimensional model using CAD. They are used in analysis the most. So there are three types: one-dimensional, two-dimensional, three-dimensional. The actual models are shown here. The geometric property is defined by the nodes. In one-dimensional element it is length, in two-dimensional element it is area, and in three-dimensional element it is volume. So the nodes and elements should be numbered after discretization process. So numbering process decides the size of the stiffness matrix and it leads to the reduction of memory requirement. So there is a condition in numbering the nodes. Maximum node number minus minimum node number is equal to m minimum. This is the condition. Consider the right side figure. You can see element A which have 4 nodes, and maximum node number is 5 and minimum node number is 1. So maximum node number minus minimum node number should be a minimum. So this is how we will number the nodes and elements. So the right side figure just shows an structure which is divided into 3 elements and nodes are marked. And after numbering of nodes and elements, we will select the displacement function which involves choosing a displacement function within each element. And generally the solution or interpolation model is in the form of polynomial. And after selecting the displacement function by using strain displacement relationship and stress strain relationship. Strain displacement relationship, E is equal to du by dx, where u is the displacement and e is the strain. The stress strain relationship, you already know, stress is equal to Young's modulus into strain. By using these relationship, we will define the material behavior, and after defining the material behavior for each element, consider a structure having 3 elements. For all the 3 elements, we will derive elemental stiffness matrix. We will define the stiffness matrix, we will derive it, and we will get equations based on that stiffness matrix. So if we consider 3 elements, we will have 3 different stiffness matrix equations. And after that, we will assemble those elemental equations into a single global total equation. So and it will be in the form F is equal to K into U, where F is the global force vector, K is the global stiffness matrix, and U is the global displacement vector. After attaining the global equation, we will apply boundary conditions. So boundary condition involve substituting some known values of parameters under consideration at some known points into the assembled global equation. And after applying boundary condition, we will get the solution for unknown displacement, and after getting the unknown displacement, we will compute the strain and stress related variables, and at last we will interpret the result. So the interpretation result is a post-processing stage, and after post-processing we can frame and display in vector or raster form as desired. These are the general steps in FEA. This is very important. You should study the steps in detailed manner. So let us see what are the software packages for FEA. There are different software using in different conditions. Some of them are ANSYS, Nastran, Abacus, Cosmos, Patron, Hypermesh, Dyna3D. So you should know the software packages of FEA, to name a few at least. Now let's see the advantages of FEM. What are the advantages of FEM? FEM can readily handle complex geometry. That is one of the major advantage of FEM. It can handle complex analysis and complex loading. Indeterminate structures can be analyzed by using finite element method and can handle bodies comprised of anisotropic and non-homogeneous material. Anisotropic material means the materials in which properties such as Young's modulus change with direction along the object, such as composites. And special material effects are handled such as temperature dependent properties, plasticity, creep, etc. These are the advantages of FEM, and some of the limitations or disadvantage of FEMs are high computational time is needed, and experience and judgments are needed in order to construct a good finite element model. A powerful computer and reliable FEM software are essential. Sometimes input and output data may be large and there occurs some numerical errors. These are the disadvantages of FEM. So the finite element technique has over the years been so well established that today it seems to be one of the best method for analyzing the efficiency of a wide variety of practical problems. So FEM is used in variety of fields. So you should study what is FEM, what are the general steps in FEM, what are the software packages of FEM, advantages and disadvantages of FEM. In the next section, we will study about the shape function and formulation of the stiffness matrix and some simple problems related with one-dimensional bar elements. Thank you.